Okay, we are we are we are starting our today's lecture. We will discuss today polar molecules. We will discuss the polar molecules and then Langevin Debye formula. We know that a polar molecule has a permanent dipole moment. We have discussed it in our previous class that a polar molecule has a permanent dipole moment. Means that a molecule that has already polarized means two type of charges. One is a positive ion and second is a negative. Means electronic cloud is always present there in the absence of the applied electric field. That is the polar molecule. And a polar molecule consists of at least two different species atoms. What are these two species of atoms? For understanding, we consider that if a molecule that can consist of more than one atom is polarized, then positive ions and negative charges will be separated with some distance, and make it will create a two species of the atoms. And during molecular formation, some of the electrons may be completely or partially transferred from one atomic species to the other, with the resulting electronic arrangement being such that positive and negative charge center do not coincide in the molecule. It means that when a molecule is formed, then some of the electrons may be completely or partially transferred from one atomic species to the other. Means electrons can be transferred from one atomic places, means a cloud of charges to the another cloud of the charges. That cloud of the charges consists on the negative charge, means electrons. And what is the result of that transformation? Result is that electronic arrangement is like such that positive and negative charge center do not coincide in the molecules. Means their center is not the same. The center of both positive and negative ions charges is not the same after this formation. In the absence of an electric field, a microscopic piece of the polar dielectric is not polarized. Means when you do not apply an electric field, then a microscopic piece of the polar dielectric is not polarized. Since the individual dipoles are randomly orientated as shown in figure 5.3, you can see this figure that atoms are present at different places, and this is a random distribution of the permanent dipoles. Although the whole dielectric is not polarized, but these individual atoms are in the form of dipoles. Means they have the separated positive and negative charges. And the polarization of such a figure, such an arrangement, has been defined in our previous classes that P is equal to 1 over delta V sigma Pm, means dipole moment per unit volume. This is the total polarization of the such type of arrangement. And this summation extends over all the molecules in the volume element delta V. And the Pm means dipole moments are oriented at random, just like in figure 5.3. Their arrangement, their orientation, their direction is random because there is no applied electric field to this material. That is why their orientation is random. If if the polar dielectric is subjected to an electric field, means this piece, this one, is placed in an electric field, the individual dipole experience torques that tend to align them with the field. Means that a torque is experienced by these dipoles, means orientation. A rotation in these dipoles is experienced, is felt, and thus orientation is towards the applied electric field. Direction of that orientation is aligned with the applied electric field. If the field is strong enough, the dipoles may be completely aligned and the polarization achieves the saturation value. Means you apply a strong electric field. If you apply the strong electric field, dipoles will be completely aligned in a direction. In what direction? In the direction of the applied electric field. And the polarization of these dipoles becomes the maximum, achieves the saturation value. And what is that saturation value? That is Ps is equal to npm. N is the total number of molecules per unit volume. So we have obtained saturation polarization. We have achieved the saturation value of the polarization, which is that Ps is equal to npm. So now we come to the next point. We can leave these two paragraphs and we can come to the in the next page, that we will start from the equation 5.18 on the page 134. The potential energy of a permanent dipole P naught in an electric field Em is U is equal to minus P naught dot Em. Means this is the potential energy of the permanent dipole. What is that? U is equal to minus P naught dot Em. Em is the electric field, P naught is the permanent dipole. And this dot product can be solved like it is equal to minus P naught Em cos of theta. Minus P naught Em cos of theta. where theta is the angle between P naught and electric field. Theta is the angle between dipole moment and applied electric field. The effective dipole moment of a molecular dipole is its component along the field direction. So the dipole moment tries to align itself in the direction of the electric field, and the component of that dipole moment that is in the direction of the electric field, which is P naught cos of theta. Using the Boltzmann relationship, we find the average value of this quantity to be P naught cos of theta is equal to, remember that this P naught cos theta is the effective dipole moment that is in the direction of the electric field, and its average value is obtained by this equation 5.19, that is integral P naught cos of theta e power plus P naught em cos theta by kt d omega over integral e plus P naught em cos of theta by kt d omega. This is our equation number 519. Here d omega is an element of the solid angle that may be replaced by the 2 pi sin theta d theta, and the limit on theta are 0 and pi. Means our solid angle d omega is equal to what? 2 pi sin of theta d theta, and theta has the range from 0 to pi. The minimum value of the theta will be 0 and the maximum value of the theta will be pi. And we know that P naught, Em and Kt are constant in the integration. The integrals may be readily performed, and we put a convenient form in equation number 5.19 to make the equation more simple, that y is equal to P naught Em over Kt. In equation number 519, in the exponential factor, we can see the value of P naught and Em over Kt. So we replace this P naught Em over Kt with y. Then equation number 519 will become average value of P naught cos of theta is equal to P naught into cot hyperbolic y minus 1 over y. So this equation number 519 will be modified after putting this value in that equation and solving for the integrals. So this equation 5.21 is called Langevin formula. This equation 5.21 is called the Langevin formula. And plot of this function is given in figure 5.4. We can see the figure 5.4 on the next page, on page number 135. We can see that on the x-axis the value of y is given, and on the y-axis the value of 1 over P naught, means average of the P naught cos of theta is given. This basically plot is obtained from equation number 5.21. From equation 5.21 we see that P naught is being multiplied on the right hand side. If you bring it on the left hand side, it will be divided to the P naught cos of theta. So average value of P naught cos of theta divided by P naught will be equal to cot hyperbolic y minus 1 over y. So this P naught cos of theta over P naught is on the y-axis and value of the y is equal to P naught Em over Kt. This is on the x-axis. So in this graph, value of electric field, temperature can be changed. Others are constant. And the plot is given for the Langevin function. And we see that the asymptotic value as y tends to infinite is 1. Means if you increase the value of y from 1, 2, 3, 4, 5 and so on up to infinite, if you touch the value of y to the infinite, then the value of 1 over p naught cos of theta remains constant. What is that? That is equal to 1. So in this graph, we can see that in the beginning, it's a linearly increasing. But after getting the value of 1 on the y-axis, it becomes constant. Means from this figure, equation 521 does indeed give a saturation effect at large field strengths. In this sentence, the author says that if you increase the value of electric field E, then ultimately y will be increased, and after increasing y, the value of 1 over p naught into p naught cos of theta will become constant after getting the value of 1. So it will be saturated. At small value of y, however, the curve is linear. At small value of y, the curve is linear. Yes, we can see from this figure that approximately up to value of 4 to 5, up to value of 2, y is equal to 2, this line is linear. After 2 to 5, it is linear, it's exponentially increasing, but after 5 it becomes constant, its value becomes 1. And this linear region is important at ordinary temperatures. Now we come to the next point. In the next paragraph, since it is the linear region of the linear region of equation 5.21 that is important, it is appropriate to expand cot hyperbolic y in a power series and keep only leading terms. Mean if you increase the value of y, it becomes constant, and you expand this y in a power series, just like we have a binomial expansion, and we also have the power series. And ignoring the higher terms, leading term means higher terms, the first term cancel at last term in equation 521 with the result that P naught cos of theta is approximately equal to 1 over 3 P naught y. And the value of the y is P naught square Em over 3 Kt. So after putting the value of y in this formula, in what? in 1 over 3 p naught y. Just put the value of y from our previous equation number 5.21. The value of y is equal to p naught em over kt. It will become p naught square em over 3 kt, because p naught is present here, and 1 p naught from the equation 5.20, it will become p naught square into em over 3 kt. And this term, average of p naught cos of theta, is average effective dipole moment. Therefore, the polarization p is equal to n p naught cos of theta and has a direction of the em. P naught cos of theta is the average effective dipole moment. Yes, its effective dipole moment in the direction of em. And for the n number of molecules, this polarization becomes p is equal to n p cos of theta. Therefore, the equation 522 may be written in the form of 1 over n p is equal to p naught square over 3 kt into em. Means you just write the left hand side is equal to 1 over n p. P is the total polarization. From a comparison of this equation with equation 5.8, we know the equation 5.8 is. Did you understand how this equation 5.22b is obtained from 5.22a? We have just replaced p by n into p naught cos of theta. P naught cos of theta will be equal to capital P over n. Just so put in equation number 528 this value of P naught cos of theta is equal to P over n, this one. It will become P over n is equal to P naught square over 3 kt em. Then from a comparison of this equation with 5.8, what is the equation 5.8? It is Pm is equal to alpha Em. Pm is equal to alpha Pm. We have studied in our previous lecture that Pm is equal to alpha Em. Alpha is polarizability, Em is the electric field, Pm is the dipole moment. We know that alpha from this equation will be P over Em. Here we have P over Em. It is evident that the polarizability alpha, that is molecular dipole moment per unit field, is mean from equation number 5.8, this is here, this one, Pm is equal to alpha Em. Alpha will be equal to P over Em. Alpha will be equal to P over Em, and we will put the value of P in this equation 5.8 here. Then alpha will be equal to P over Em is equal to P naught square over 3 kt. Em will be cancelled out with the Em of equation 5.8. We will put the value of P from here in equation number 5.8, and then alpha will become P naught square over 3kT. This result has been derived by neglecting induced dipole moments. Means our our previous yesterday's topic we studied the induced dipole moments. These has not been considered in this derivation and represents what we might call an orientation polarizability. So this alpha is called the orientational polarizability, means the polarizability due to the applied electric field and orientation produced in this dipole moments. Induced dipole effect give rise to what might be termed a deformation polarizability alpha naught. It means that if you consider the induced dipole effects in this equation 5.23, then it will give another term, that is deformation polarizability alpha naught. And after considering this alpha naught, the general case of the total molecular polarizability will become alpha is equal to alpha naught plus P naught square over 3kT. This will be our equation number 524, and this expression is known as Langevin-Debye equation. This equation is known as Langevin-Debye equation and has been of great importance in interpreting molecular structure. Means when you study the molecular structure, then this equation plays a very important role because it provides you the information of the polarizability of the material. Mean if on the applied electric field, how much polarized this material will become at what temperature. Here we have a capital T. This is a temperature. So the effect of temperature on the polarizability is also discussed in this equation number 524. So this was our today's lecture. If you have any question, you can ask me. You can ask me the question over here. I'm present. And if you have, you can send me the question later on if you have in the question in the after this lecture. I will answer you and in the description. No question? Okay. Thank you very much, you guys, for listening to the lecture. And I hope you have enjoyed this live streaming. You can subscribe and you can ask me question later on. Thank you very much.